All right, guys. Last part of Unit 5, our electrons chapter. The last thing we're going to talk about is periodic trends. We sort of started off the unit talking about the periodic table, and we're going to sort of wrap it up by talking a little bit, now that we know about electrons, about some things that we can tell just by looking at the periodic table. Okay, so take out your periodic tables. You might want to record some notes on this real quick, and here's what we're going to talk about. A periodic trend basically is just some property of atoms or elements that changes as you go either from left to right on the periodic table or from top to bottom on the periodic table. So we're going to refer to everything in these ways. We're going to say that something increases going from left to right, that it decreases going from the top to the bottom, or vice versa. Okay? So what you're really going to have to do here for this section, and it's pretty easy, is just make sure that you know what the term means in each case, and then know how it relates to the periodic table. Okay, pretty straightforward. There's no math or anything here really, although there are numbers involved, but we're not going to do the numbers. But you just need to sort of look at this. This is also the thing that if you go to ptable.com, you can sort of click on each of these things and they'll give you a great graphical representation of everything. Okay, so first thing, and this is kind of one of the big ones, is atomic radius. Atomic radius basically means the size of the atom. Okay, how big is the atom? And here's the way it works. As we go from left to right on the periodic table, it is going to decrease. It's going to get smaller. Now that seems weird, but let me show you why real quick. Let me just take a real quick example here. So let's take lithium and fluorine. Okay? So we'll come back here so you can do the definition. If we've got lithium and fluorine, though, their highest energy level for both of them is 2. So in both cases, you've got something sort of like this. Okay, you've got a nucleus in the middle. Okay, and then you've got 2 energy levels around that with electrons. Now, in the case of lithium, you've only got 3 total electrons. Okay, in the case of fluorine, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 total electrons. Now, the way I drew them is a little deceptive because it looks like fluorine's a little bigger. Actually, though, fluorine is going to be smaller, and here's why. I've got 3 protons in the nucleus here, and they're pulling on these 3 electrons in the lithium. Okay, so basically they've got, like, you could assume that it's like an attraction together of 3. If you look at fluorine, though, they've got an attraction together of 9. There's 9 protons in the nucleus and 9 electrons on the outside, and so what that does is it just pulls it in tighter. There's an attraction level of 9, and so it's going to shrink that fluorine atom down and just make it a little bit smaller. They both only have 2 shells, but what's going to happen is fluorine's shell is actually going to be a lot smaller. Okay, so that's the left to right part of this. The top to bottom part is that every step you go down the table, it's going to get bigger, and that's because you're adding another energy level. So just to use the same sort of examples that we just used, okay, lithium, okay, 2 shells, all right, and then right below that is sodium, and sodium, I'll put a nucleus in there real quick, sodium has 1, 2, 3 shells, okay, and if you went down to the next step to potassium, then you're going to have 1, 2, 3, 4 shells, and it's going to get bigger and bigger each step as you go down the table. Okay, so what does that mean for us in terms of periodic trends? Well, here's what I would say that you should probably write. Just make a little note. It says atomic radius, or size, if that makes you feel better. Okay, atomic radius. And as I go from left to right, what does atomic radius do? It goes down. As I go from top to bottom, what does atomic radius do? It goes up. Okay, we'll come back and fill in some more stuff on the table here in a second. We talk about the other terms. So second term, this is a pretty big one for us. Ionization energy. Ionization energy is the energy required to remove 1 electron from an atom of an element. But what that really means is how hard is it to pull an electron away? Okay, there's an energy required to pull an electron away. And remember we talked in the last unit about the fact that metals, things to the left of the staircase here, have positive charges. And what that means is that it's much easier for them to give up their electrons. We said the stuff over here on the right-hand side, they form negative charges, and that means they don't want to give up their electrons. They want to gain electrons. Okay, so how does ionization energy work then? Well, ionization energy, okay, and we'll call that IE, Okay, ionization energy, then, if it's harder for stuff on the right-hand side, that means that ionization energy is going to increase going from left to right, and it's going to decrease as we go down the table. Now, there are reasons for that. Basically, these are closer to 8, so they don't want to give up their electrons. They want to gain them. These are further away. If they lose them, they'll have 8. And then as you go down the table, it becomes easier to pull the electrons away because they're further away from the nucleus. Okay, if you're 7 steps away, then it's much easier to break free of the nucleus than if you're only 1 step away. Okay, so pretty straightforward there. Electron affinity, I don't really like this term a whole lot. We're going to use a lot more electronegativity that we'll talk about here in a second. But basically, electron affinity is how much energy, what's the energy change when an electron is given, to a neutral atom or is acquired by a neutral atom. And what it means is whenever you see the word affinity in any context, not just science, affinity means how much does it like them. So how much do they like electrons? Okay, so electron affinity basically increases as you go from left to right. Okay, stuff over here wants electrons more. Again, why? Well, look at the halogens here, fluorine, chlorine, bromine. They have 7 valence electrons, so if they get 1 more, they'll be noble gases. So they really want electrons. They have a high electron affinity. On the other side, as we go down the table, okay, electron affinity is going to decrease in general. Okay, further away from the nucleus, they're gonna it's easier to pull stuff away from them, and so they don't have as much affinity for the electrons as before. This is going to be related to a term that we're going to talk about here in just a second that I think is a whole lot more important. Okay, ionic radii, this is pretty much the same thing as atomic size. They always make you learn this differently, and I don't know why, because they basically work in the same way, which is that as you go from left to right on the periodic table, the ionic radius is going to decrease. Okay, they're going to get smaller. You're going to lose, like for your cations, they lose electrons, and so they're going to get smaller. You're going to have less attraction, or more attraction, when you go from left to right, and so the ionic radius is going to decrease. And then as you go down the table, ionic radius is going to increase in general. Now, these are sort of general trends. This doesn't always apply. You can have two things that are next to each other and be a little bit different than this, but in general, that's the way it works. Okay? And our last big definition is something called electronegativity. I like this term a lot. We're going to use a lot of electronegativity when we talk about bonding, when we talk about molecular geometry and polarity and all that stuff. It's all about electronegativity. And electronegativity sounds a lot like electron affinity, and it sort of is. The main difference is that if you look in the definition, it's the ability of an atom in a compound to attract electrons. It's not, strictly speaking, an energy that's gained when that neutral atom does get the electron. It's just how much it wants to have electrons, okay, is electronegativity. Basically, how much does it pull electrons to itself? And this one's pretty easy. Again, electronegativity increases as we go from left to right, and it decreases as we go down. And we've already sort of said that. Stuff on this side of the table really wants electrons. Stuff on this side really doesn't. Now, here's the deal. Noble gases are typically an exception to all this stuff. Noble gases don't want electrons, okay? They don't want to give them up either, but they don't really need any because they're already at 8. They already have 8 valence electrons, so they're pretty happy. But here's sort of the kicker here. Here's what's really important. Fluorine. Fluorine has the highest electronegativity. Okay? And so what that means is, I think instead of just memorizing the arrows for electronegativity, what I keep in my mind all the time is just that fluorine's the highest, and the further I get away from fluorine, the lower it gets. So fluorine's highest, oxygen and chlorine are next, and then as I start to move away from that, I start to get less and less electronegative. And that's going to matter a lot when we get to polarity here in a little bit. Okay? So let's go back, and hopefully you've been marking these in, but let's just go back real quick, and let's just write all of the stuff that we had here up. So ionization energy, remember, increases from left to right. Okay, and this is sort of a summation here. It's going to decrease going down the table. Our next thing here was electron affinity. Okay, so electron affinity whoa, let me erase that. Sorry, guys, that was some bad writing. Okay, electron affinity is going to increase going left to right. Electron affinity is going to decrease going down the table. Okay. And then we had ionic radius. Ionic radius is going to decrease from left to right. and then it's going to increase as we go down the table. And again, that's pretty much the same thing as atomic radius. Those two things are pretty similar. Okay, and same sort of reasons. The ionic radius is going to increase because we're increasing energy levels. Okay, and then the last one, which is sort of my favorite, to me the most important one, electronegativity increases as we go from left to right, and it decreases as we go down the table, and really most importantly is that fluorine is the most electronegative thing. Okay, I know that that's sort of a lot of stuff, but really the rules are pretty simple, and if you do, you can easily set yourself up some flashcards or something, guys, to say, hey, what does electron negativity do from left to right? And just run through those flashcards real quick. And the way you're going to see these on a test is you'll see them compared to each other. So I might say something like, okay, you've got two things. You've got fluorine and sodium. Which one has the higher electronegativity? And you're like, okay, no problem. Fluorine always has the highest. Which one has the bigger ionic size? Well, sodium is in level 3 and fluorine's just in level 2, and so that means the sodium's going to have the bigger size. And I know what you're thinking. You're thinking, but didn't you say atomic radius decreased as we went from left to right? It does, but the going down the table matters a lot more than going from left to right. So sort of keep that in mind as you're working all these out. And we'll work a bunch of examples in class. So you just sort of need to memorize those rules real quick. And they're pretty easy. Know what the words mean. Know how it changes as you go across the table. All right? Thanks, guys.